Hi, everyone. This is Jonathan from Facebook and Reddy from Intel. We are going to give Xeon scalable processor Coreboot status update with focus on the features. The agenda is we will talk about the status of the Facebook open source open system firmware first, and then we give a Intel FSP overview, and then the Coreboot FSP status. Then in the end will be summary and next steps. So this is the same slide we saw in the other presentation, that for on the compute platform, we went through 3 generations. Now we are at the 3rd one. We are working in progress on Delta Lake, which is based on Cooper Lake scalable processor. This is a screenshot of the Skylake SP FSP proof of concept. It demonstrated a working Coreboot solution. It's a POC quality of the FSP. And the Coreboot code is upstreamed. And we can see 2 sockets and all the CPUs comes up. The Cooper Lake SP-FSP bring up is in progress. We can see that is a 1 socket server with 26 cores, 2 hyperthread per core, so 50 CPUs. And then there is the Coreboot documentation for Delta Lake.
Jonathan, real quick, can you go ahead and flip into presentation mode for us so it's full screen for our audience?
Sure.
Thank you.
No problem.
Uh-oh. Ah.
Trying to figure out how to flip.
It's just at the bottom, that little,
right. Yeah.
right to the left,
Left, yeah, down.
That little desk. Yep.
Yeah.
Thank you. Thank you. Ready?
All right. I'm sure you guys are getting bored with this slide. I kept this one primarily for folks who haven't seen this before. You heard throughout the the morning talks, afternoon talks about Intel firmware support package. In a nutshell, when it comes to Coreboot, we will be using and we are using Intel FSP as really the key component that does the processor, chipset, memory initialization through the binary interfaces, and those binary interfaces are defined through UPD, and that we get the data from the FSP using hobs. So UPD and hob are the primary interfaces that we use with Intel FSP as a way to actually do the core initialization, the portion. Next slide. Okay. So here is a click down of what FSP does. If you're familiar with the client side FSP, it's not really the same as server side FSP. There are significant differences between the server FSP versus the client CPU FSP. The big one is obviously Xeon SP is a multi-socket platform. In this picture, we are talking about a 2-socket enumeration, but you may have 2-socket, you may have 8-socket, or you may have 1 socket with different topologies that actually connect multiple sockets, which we call that as the UPI link between the 2 sockets. So the first and foremost, when you actually initialize the the FSP Coreboot through FSP, it has to actually not only bootstrap but also do the KTI initialization, discover the other sockets that are actually connected to the bootstrap socket, and then discover all the cores that exist on the remote sockets through the KTI training. And then it also has to do the memory training to be able to discover local DIMMs local memory as well as the remote socket memory. So that's one of the key components in the FSP initialization on the server platform, unlike the client platforms. The MRC in general is fairly complicated, as most of you are aware. So part of the focus is to really, the abstract the complex initialization portion through the FSP, and then have the MRC, logic implemented in the memory unit and the silicon unit, phases of the FSP. And then there is the early and late integrated IO initialization, essentially looking at all the IIO stacks that exist on each one of the sockets, and assign the bus starting and end numbers, and then actually assign the bus windows. Right. So those are the three big areas that FSP actually is different from the client-side platforms. Next slide. So here are the Coreboot extensions. It kind of mirrors what we have in the previous slide. We have to do something similar in the Coreboot to be able to enumerate multiple sockets and the cores, and then actually extract the APIC IDs. So the multi-socket device enumeration and configuration has been one of the key focus areas when we brought up Skylake two-socket SP platform. Some of the challenges we had in the beginning were mostly to do with the timeout. When you actually go and do the AP discovery, the timeouts were not enough for the server platform. So we had to actually modulate some changes to the timeouts so that we can enumerate all the cores on all the sockets. And then there is per thread configuration that is needed on the Xeon. The MSRs are slightly different compared to the client platforms. So we essentially have to look at things like the turbo ratios as an example, and then make sure we program them as part of the multi-socket device enumeration and configuration portion of the Coreboot logic. The second big one is the integrated IO. On the Xeon platforms, every root bridge essentially has its own MMIO window space, the bus range and an MMIO window space. We essentially have to enumerate the PCIe devices, do the bar allocations that actually align with the IIO stack windows. Most of the work in the second half of this year has been some fine tuning and optimization for allocation above 4 GB, prefetchable and non-prefetchable memory allocation as well. And then there is a 32-bit and 64-bit, memory, address mapping as well. So quite a bit of work in the second half of this year on the IIO enumeration, specifically the prefetchable and non-prefetchable portion of the enhancements. ACPI NUMA tables, most of the work that we have done from the past update in the beginning of this year has been around ensuring that the DMAR setup, as well as the IIO stack related SRAT and SLIT configuration works on the Cooper Lake platform. So there is a bit of a Cooper Lake specific platform changes needed on the ACPI front. So that was a third change. As you heard in the morning talks, SMM optimization for the the Xeon, where you have significant number of cores compared to client platforms. So you do need to optimize it so you don't get into timeout issues. Some brass work that is currently going on, and then also the power management aspect. Next slide. Here is the click down on the device IIO stacks. So if you look at the left-hand side, Cooper Lake CPU essentially has the CPU bridge, and then there are a bunch of PCIe root bridges. Each one of them will have its own bus base as well as the bus range. And then you have to actually go through the enumeration for each one of them. In the Coreboot implementation, it essentially follows the flat device enumeration, and it assumes that it is, all the devices are hanging off of CPU bridge. And it, allocates the memory windows, based on the initial range that is available, which is pretty much configurable, but it assumes that that is the only range where you are allocating the bar address ranges for these devices. So that model will not work for Xeon. So we essentially have to extend that model to enumerate all the devices in each one of this, the stacks, and then we need to assign the bar windows based on what the bar windows are from each one of those, the stacks as well. That's what you see on the right-hand side, which is essentially a set of changes needed on the Coreboot to support the multi-route PCIe bar allocation, both for prefetchable and non-prefetchable windows. Next slide. So here is essentially the hub. So how are we getting these windows? Like I mentioned in the beginning, the primary interface to FSP is either UPD, when you actually call memory init, temp parameter, or the silicon init, and then hub is essentially the other mechanism to extract all the data related to a specific, the processor configuration. So all the IIO stacks that we have here, we essentially get through the IIO hub, which essentially is a very critical component for most of the ACPI table, the stitching. On the right-hand side, you can actually see the IO base and the limits for each one of the stacks. And then there is a MEM32 base and limit. And there is also 64-bit base and limit. And then you also have the VTD bar address for each one of those stacks. So we use this information, which is actually in the next slide, to be able to stitch together the ACPI tables as well as PCIe bar configurations. And if you look at the Coreboot device tree, Coreboot device tree essentially gives you a very flat PCIe hierarchy, which is on the left-hand side, hanging off of the host bridge. When you extend that with the device tree enumeration in the previous slide, with that logic, using the hubs, you essentially get into, PCIe devices that are actually enumerated for all the IIO stacks, which is what you see on the right-hand side. Okay, next slide. Here is the board integration. So most of the work on the Yosemite V3, which is essentially the chassis for Delta Lake board, which has the Cooper Lake one socket CPU on it. Majority of the focus on the Delta Lake has been obviously the GPIO settings, but the other focus has been what is the best way to enumerate, configure the IIO bifurcation rules. There are wide variety of device configurations on this board. We needed a mechanism to provide at runtime what configuration options we want for the PCIe root ports and the bifurcation settings and the number of lanes. So these three attributes are very, very critical for any new board bring up: GPIO settings, PCIe port settings, as well as the bifurcation rules. Next slide. Okay, so I kind of touched upon the firmware support, the nuances involved for the single socket, multi-socket Xeon SP platforms, and the things that are needed on the Coreboot front to support the Xeon SP processor, and what we did on the Delta Lake board. The plan, Facebook plans to actually take this forward over the course of next year for specific maintenance type of use cases, so that we get an early indication of how the Coreboot is actually functioning for production maintenance use cases. Now, going into 2021, we do want to wrap up the Cooper Lake effort, both from the Coreboot bring up changes as well as the platform bring up for the Delta Lake, and then make the FSP binaries available in time for broad community, the contributions and development, as well as OCP logo, and the compliance portion of the work starting next year. Beyond that, we want to target in enabling the upcoming Xeon SP processors, and that will be the focus starting early next year. Next slide. Here are the two platforms: OCP Tioga Pass 2-socket server, which is open inspired and open accepted. And then the next one, that Jonathan actually covered in the afternoon talk is the OCP Delta Lake Yosemite V3 one-socket server. As Jonathan mentioned, they are looking at pushing the OCP Delta Lake specs into OCP at some point next year once they go into MP, which is mass production. Next slide. The big ask from the community is do contribute to any open system firmware. It doesn't have to be Coreboot, and essentially help us bring Xeon SP based processors on the open system firmware and OCP platforms. That's one key ask. The second thing is, as we get into next year, we will be looking for more and more, advanced server features. In the morning, I talked about Compute Express Link. It essentially brings in very interesting dynamics to the platform. It expands several use cases, accelerator, caching, and memory buffer type of use cases. There is quite a bit of work that is needed on the Coreboot front to enable CXL attached devices. RAS is one of the key components. We want to look at essentially figure out the best way to support the OS first model, where the RAS is actually monitored via the OS kernel drivers, and then look at what is the best way for us to support the firmware first for specific RAS features where we still need that for the runtime SMM functionality. And then ACPI stitching, specifically for the persistent memory hot plug type of functionality. We don't have that in the ACPI today, and we want to be able to support those. So there will be some work in the ACPI table setup, testing, validation on the specific platforms. Then the next focus would be the continuous integration testing and automated testing. This is the area where we spend a lot of time when we do the board bring up, looking at the stability aspects, recycles, and then see if we can actually get a very consistent, reliability across, let's say 50 to 100, recycles. And then also looking at all the settings and make sure everything is working through the recycle test cases. So we want to make sure that we can automate as much as possible to bring up the platforms very quickly. So there will be a lot of focus on the automated testing aspect as well. With that, I conclude my talk. Thank you. Open for questions.
So it might be worth, this is a terrific talk, by the way. It might be worth trying to find out like how to tell people how they can get involved, because there may be some people here who haven't worked at this level with OCP hardware. So what would their first step be? Where would they go to look for things to get? What would they do?
Excellent question. I think the starting point would be obviously looking at the Delta Lake board and the Delta Lake specs and the Coreboot side of the contributions. The second thing is obviously having a Xeon platform. Purchasing that is going to be super expensive. That is one area where the Philip and company actually shared how they are doing the continuous integration testing. We probably have to piggyback on some of that to be able to test on a real platform. Obviously, you can have your own platform and test it out too, but that is probably super expensive for most of you. That could be an option to test out on a real platform. The third thing is, obviously, if you have once we get the FSP blobs available and header files available, we don't have to do this roundabout way of having the dummy blobs and then actually submitting patches. So we will be essentially getting out of that mode. The fourth one, obviously, you can reach out to me, Jonathan, And there are several folks who actually contributed to the Coreboot Xeon SP work. That includes 9-Elements team, CISPRO team, Google team, and then obviously Quanta and Weavin. So we have, team of experts who have been very familiar with how to, develop code for the Xeon SP and server-side platform functionality in Coreboot. You can always reach out to them to seek guidance, help, collaborate, contribute, partner, whatever is the convenient mechanism, but we are here to help you to actually start contributing to the Coreboot.
And a quick question, I didn't hear any other questions. Sorry to ask again. Do you have a link to this talk that I can share with other people at Google?
It should be publicly available, right? We uploaded this one, Ron, so.
Sounds good. Good to hear.
I can send you the PDF too, right? Either way, whatever works.
Yeah. If you want to send me the PDF, I won't turn it back, and I'll go look for the talk too. Thanks.
Yes. Okay. Both are options.
Yeah, Ron, those are all public information or went through internal review, so those are good.
Yeah, this is just amazing. This is really very, very interesting talk. Thanks.
Thank you.
So Jonathan, anything else you want to highlight?
No, I think
Delta Lake specs or anything that you want to talk to?
I think you summed up very, very well. Yeah. So yeah, one way to get involved is to buy Tioga Pass, which is already available. If you already have relationship with Intel, you can get the other bits so that you can work on. Even though our focus is not Tioga Pass, but we did spend a lot of time to refactor the Tioga Pass Coreboot code with the help from CISPRO, so that we are positioned well to work on the next generation of the Xeon scalable processor, which is the work, the Coreboot work will start in 1 month. So thanks for everybody's help to review the code and give feedbacks. So I don't see any other questions. Should we wrap up?
Yep, there are no other questions in the chat right now. And we have about 2 minutes left before our next session with Christian and Philip.
Thank you, Kate, and everybody.